Okay, on to our last topic here, pH in water. Now, you guys have experimented with pH before. It has to do with how acidic or basic something is. Tested it with little pH strips that change color to determine that. But really, you probably haven't gotten into a definition of what pH actually is. So we're going to explore that a little bit. So water can break apart into ions, just like we saw salt can break into sodium ions and chlorine ions. And the ions that water forms are the hydrogen ions, this H plus right here, and what's called a hydroxide ion, which is the OH negative. And I'll write that out for you because I might say that word a lot. I want to make sure you remember what it is when I say it. Okay, so this is a hydroxide ion. Okay, so if water is separated into positive and negative charges, that's what they'll be. Those are the ions. All right, so because water does that occasionally, that affects the pH of the solution. If we have extra hydrogen ions in a solution, okay, so these excess hydrogen ions, we are going to get different types of pHs in those solutions. So the pH scale is actually a measurement of how many hydrogen ions are in a solution compared to how many hydroxide ions. So if we're at neutral, right here, there is an even amount of hydrogen and hydroxide ions. And that makes sense, right? Water itself is neutral. So if we have every single hydrogen ion bonded with every single hydroxide ion, we're going to have a neutral solution. We're going to have water. However, if we have an acid, what that really means, what's actually going on with the chemistry, is that there are more hydrogen ions than hydroxide ions. That's what actually creates an acid, and that gives us a pH reading below 7. If we have what we've been calling a base, that means we have less hydrogen ions than hydroxide ions. And that gives us a pH reading above 7. So what we're actually measuring when we measure pH is the hydrogen ion concentration. When you get square brackets like this, that means the concentration of something. So we're measuring the concentration of the hydrogen ions. And to give us that number, like 4 or 7 or 10 or whatever, we actually take the negative log of the concentration. And that will give us our actual pH number. So that's how we come up with pH. It all has to do with these hydrogen ions and what their relative proportion is in the particular solution. So here's some common pHs just to compare and remind yourself what's going on. We've got at neutral, pure water. Again, there's equal amounts of hydroxide ions and hydrogen ions, and so we've basically got water. At our very most acidic level, where we've got lots of hydrogen ions, we're going to have hydrochloric acid. At our very most basic level, where we have less hydrogen ions, we're going to have sodium hydroxide. So there's our actual pH values, with that negative log of the concentration, and that's going to be on the right-hand side. The other interesting thing I want you to see over here on the left-hand side is what's the hydrogen ion concentration. And you can see that from each step is a factor of 10. So if we go from pH of 7, which is 10 to the negative 7th ion concentrations, to a pH of negative 6, so we're going from basically pure water to urine, it's a 10 times difference in acidity. So in other words, urine is 10 times more acidic than pure water. If we go up to 10 to the negative 5, it's another 10 times. 10 times 10 is 100. So in other words, black coffee right here at pH of 5 is 100 times more acidic than pure water. Okay, this is called a logarithmic scale. So each step in the scale is a factor of 10. And so as you're thinking about moving from one pH to the other, it's not really increments of 1 that we're moving by, it's actually increments of 10. Right? So the concentration changes greatly from one pH to another. Again, just to kind of go over these in more detail, for our acids, so the acids themselves will dissociate in water again, so they break apart in water to increase the concentration of those hydrogen ions. So acids have many hydrogen ions in them. That's kind of a review from what we said before, and they tend to have a sour taste. Bases, on the other hand, combine with hydrogen ions. So those hydroxides, those OH ions, OH negatives, will combine with extra hydrogen ions, so they'll decrease the hydrogen ion concentration because all those hydrogen ions are getting bound to or bonded up in the hydroxide ions, the negative OHs, to make water. All right, so because of that, there's less hydrogen ions, and remember, pH is a measurement of the concentration of hydrogen ions. If there's less concentration, that means it's more and more of a base. Again, it comes from lots of hydroxide ions, many OH negative ions, and they tend to have a bitter taste. All right, last topic for this one, something called a buffer. Buffers are really important in life, in living organisms, but also in experiments that we do in biology. What they will do is summed up right here in the first statement. They act as a reservoir or a storage place for hydrogen ions. And here's what's important. They will donate or remove hydrogen ions from a solution as necessary. So if you are working with a solution in lab that you don't want to be changing pH really drastically, right? You want to maintain the pH as a control. You don't want that to be a variable in your experiment. You want to make sure the pH stays steady. You will use a buffer in order to absorb or let loose those hydrogen ions. We use buffers a lot when we're working with DNA, because DNA is an acid, right? Deoxyribonucleic acid, and we don't want the DNA to be changing acidity levels as we're doing experiments. So we use buffers with DNA to kind of make sure that pH of the solution the DNA is in stays steady. Again, why do we do this? Offers protection from these extreme pH levels. We want to maintain a constant pH level. We need a buffer to make sure that happens. In your blood, for example, you have buffers because you've got lots of things, as we said, dissolved in your blood, coming in and out of your blood, but you don't want the pH of your blood to be spiking up and down throughout the day. You want to maintain pretty much constant internal pH of your blood. And so you have buffers, chemicals in your blood that will absorb or get rid of hydrogen ions to maintain that constant pH for your blood.